Alright, so I'm just going to do a quick rundown of section 2 for a couple people that missed this. So your objectives in this section are to compare and contrast Bohr's model and the quantum model. So the quantum model is going to be our new model. Bohr's model was that model we used before with shells going in and out, right? And we used Bohr's model effectively to describe hydrogen. And it still works to describe hydrogen, because some of the orbitals we're going to talk about are spherical, just like those ones that we were thinking about before, visualizing before. So we just need to expand on that to get more and be able to explain what's happening with all those other elements besides hydrogen. So we're going to talk about Heisenberg's uncertainty principle, Schrodinger's wave equations, the four quantum numbers and how they can kind of be linked together to make these different ideas that we're going to use for our quantum model of the atom, right? So again, there are a few scientists here of note that come into play. This first guy, I know his name looks kind of funny, but it's pronounced Dubois, right? He was the one that proposed that electrons have wave-like properties. So again, remember we saw that diffraction, that interference on the video that we watched. We know that electrons interfere with each other, which means they have to behave like waves. Right? Heisenberg stated that it's impossible to determine the position and velocity of an electron simultaneously. Right? Again, that video talked about how maybe that electron doesn't even exist as a particle that can have an exact position until you measure it. Right? And then Schrodinger, the last guy here, yeah, he's the guy with the cat, but also he's the guy that used calculus to solve for these different solved these wave equations that laid out the foundation for this quantum theory. It was his work that actually gave us these shapes that we're going to talk about for orbitals. Otherwise, just a couple definitions here quick. Quantum theory is a mathematical description of the wave properties of electrons. Orbitals are 3D regions around the nucleus indicating the probable location of an electron. Remember, we don't talk about where the electron is exactly so much as where it could be, right? Thinking of it as a wave of probability as opposed to a single point is important. Remember, because it passed through two slits at the same time to interfere with itself. It can't possibly be a particle at all times. Right? The quantum numbers specify properties of atomic orbitals and the electrons in them. Right? So we're going to use these numbers to piece together what we think this atom looks like. So we're starting with this principal quantum number. Right? This one is actually simple. It's just indicating that main energy level. So remember when we had Bohr's atom, we had one shell, another shell, each one having more energy than the last, right? This is the same idea, right? So n, right, can be different values, 1, 2, 3, 4, 5, 6, 7, right? Whatever you want it to be, right? When n is 1, I only have one shell of electrons. I only have one energy level that I'm dealing with. That would be my first row of my periodic table, which includes hydrogen and helium, right? Electrons with the same n value or in the same shell, as it says, there are n squared orbitals per shell, right? So when I take that 1 squared, it's still 1, but then I realize that that one orbital should be able to hold 2 electrons. That's why there's 2 elements for 2 electrons in that first row, right? If I'm talking about the second row of elements on my periodic table, if n equals 2, 2 squared is equal to 4, and if I assume 2 electrons can be in each of those orbitals, that gives me 8 electrons total. And if you look at your periodic table, there are 8 elements in the second row, correlating with the 8 electrons that would be in that new shell for those elements. So these patterns begin to emerge that we can work with later. Angular momentum quantum number, right? This is where we take it a little bit further, right? This indicates the shape of the orbital itself. right? So I'm supposed to deal with n again. And then I have these values for L that I'm going to talk about. In your notes, it should be a stylized L, right? Not just a regular L. But N can be, again, 1, 2, 3, 4, whatever, right? But L is going to be, again, values of L are 0 and any positive integers less than or equal to n minus 1. Well, it turns out in this case, n minus 1, if 1 is my n value, 1 minus 1 is 0. So the only value for L in that first shell, that first energy level, is 0. Right? So there's only one orbital shape in that first shell. And we already discussed the shape of that orbital. We know that that S sublevel, that original orbital, is exactly the way that Bohr described it. It's a sphere, right? So we were using these circles that were concentric before, but it's really a sphere like a ball, right? So we knew that shape already. It's only when we get to n equals 2 that we get a new shape, right? Because 2 minus 1 is 1. So I have values for L that are 0 and 1 for my second energy level. And that introduces a new shape. Right? 1 is going to be designated as P, and that P sublevel corresponds with that P block, right, on my periodic table. So I'm talking boron through neon right now, right? But that new sublevel has a new shape of orbital that we need to deal with. So P orbitals are actually kind of dumbbell shaped, right? That's how they like to describe them. I think of it more like there's two balloons tied together at the knots, right? So it's got these two bubbles connected together at the center, right? But that's my new shape for that new energy level. Whereas when I go to n equals 3, I can go from 0 to 1 to 2 now even, because 3 minus 1 is 2, and that brings in a whole new shape, and that's going to be my D sublevel, right? The shape for those orbitals, right, as we go from D to F, right, further and further, right, those sublevels, those orbitals are a little bit too complicated to describe, right? So we're not actually worried about those shapes. We're really mostly concerned with S and P, right? So if you know that S has that spherical shape, right? We know that S, which was corresponding with 0, is spherical, right? And we know that P, that's corresponding with 1, has that dumbbell shape, right? D and F are not really all that important for us, but you do have that possibility for 2 and then 3, because if n equals 4, then I have values 0, 1, 2, and 3 to deal with. So there are 4 different sublevels with 4 different shapes of orbitals. Then we go to the magnetic quantum number, right? This indicates the orientation of an orbital around that nucleus. Again, there's a pattern here to follow. There's rules for this. Values of m are whole numbers including 0 between negative L and positive L, right? So what I'm saying is if n equals 1 again, then L was 0, and negative 0 and positive 0 are the same thing. So for m, there's only one value. There's just the 0, right? Which means that there's only one orientation for that orbital, which makes sense because no matter how you turn a sphere, it always looks the same, right? So there's a single orientation for that s orbital. So there's only one of those s orbitals, right? Whereas if I go up, if n equals 2, remember L would then be 0 and 1, and I can go all the way from negative 1 to positive 1, including 0, which gives me 3 digits, which tells me that there are 3 orientations for that orbital. All right? So when I talk about those p orbitals, there's actually 3 ways that can be oriented, right? Just imagine that xy graph plane that you use all the time for your math classes. I don't remember what color I used before, kind of purple, right? And understand that I can have an S that's oriented this way, but I can also orient it up and down on the y-axis. But then there's a third axis that we don't always think about, right? You can have Z going in and out of the board so that you could have a bubble coming out this way towards us, right? And then another bubble going out backwards behind the board. So there's a three-dimensional shape here now, right? So I have three different orientations for p sublevels, which means that there are three p orbitals. Right? And we're going to work with that more and more later. Whereas if n equals 3, remember I had 0, 1, and 2 this time, so that means I could go all the way from -2 to +2, which is 1, 2, 3, 4, 5 different digits, which means that that D sublevel has 5 different orientations, excuse me. So I can take that complicated shape that we don't know, and I'll show you that later, and you can orient it 5 different ways in 3D space. Then we go to 4. Again, that's going to be 0, 1, 2, and 3 for L values. I can go all the way from -3 to -2, -1, 0, all the way up to +3. So that's going to give me 1, 2, 3, 4, 5, 6, 7 digits. So there are 7 orientations for that F orbital shape. Right? Again, it's a complicated shape, so I can't really draw it for you, but we'll look at that later. So again, the magnetic quantum number just tells us the orientation. It actually tells us how many orbitals are in each of those sublevels. So there's 1 s orbital, there are 3 p orbitals, there are 5 d orbitals, and 7 f orbitals, which is important to us. Finally, the spin quantum number indicates the fundamental spin of an electron in an orbital. If 2 electrons are in the same orbital, they have to have opposite spin, right? That is the key that you need to look at on this slide. All I care is that they have opposite spin states. Because if they had the same spin state, they would interfere with each other, right? And remember, they're waves, not just particles. Interference would make them disappear. Right? They would be kicked out of that orbital if they were in the same spin state. So, for our purposes, we don't really have to worry about the numbers, the -1/2, +1/2. All we need to understand is that when we represent electrons later in an orbital that we're just going to draw as a line, if one's got a spin in one direction, the other one's spinning the other direction. Right? That way they can occupy that same space without interfering with each other. So each orbital contains 2 electrons, but they always have opposite spin. So just focus on that for this quantum number. So then when we're done, right, we can put all these numbers together to create a pattern that emerges, right? If n equals 1, remember there's 1 sublevel in that first energy level. It's that S sublevel, right? There's only 1 orientation for that sublevel, so there's only 1 orbital in that first energy level. So that means there's 1 total orbital over here. But again, there's 2 electrons per orbital. So there's 2 electrons in that first energy level. If I go to n equals 2, now I have 2 sublevels, S and P, right? The original S had 1 orbital, but P has 3 orientations, so there are 3 orbitals. So my total orbitals for my second energy level is 4, and I can double that again to know that there are 8 electrons in that second energy level. Simple math, but it keeps building, right? So n equals 3, there should be 3 sublevels now, S, P, and D. So 1 orientation for S, 3 orientations for P, 5 orientations for D. That gives me 9 total orbitals and 18 electrons total in that third energy level. Again, these are things that we should recognize off of a periodic table. There are 18 groups, including that D block in the middle, right? Total, there are 18 columns across your periodic table for a reason, because there's 18 electrons in that third energy level. Finally, I have my fourth energy level. That has 4 sublevels, S, P, D, and F. Right? There's 1 orientation, 3, 5, all the same as before. But now I have those F sublevel orbitals, and there are 7 of those because there's 7 orientations for that shape. Add that all up, and I get 16 orbitals total, and that gives me 32 electrons in that 4th energy level. So again, we're looking for these numbers later. We're looking at these patterns, right? 2, 8, 18, 32, those will emerge very clearly as we continue to go through this and talk about this model for the atom that we're going to ultimately have. There are shortcut ways to get numbers in here, right? On that very first quantum number for n, I told you could square it, and it would give you the total number of orbitals, right? So 2 squared is equal to 4, right? 3 squared is equal to 9. 4 squared is equal to 16. So, right, we just needed all these different things to connect together and be able to explain it with math so that we could actually work with it and use it to explain how atoms work, what reactions they do, right, what properties they have. So we're going to continue working with this, but remember, even though we don't understand the underlying math of this necessarily, I don't understand it, so I don't expect you to understand it. It doesn't matter how it came to be. We know that this pattern emerges, and we can use it for a lot of things. So in the video, they talked about physicists that didn't care whether Einstein or Niels Bohr were right, and they still don't, because it works. You can use it to describe how atoms function, how they react together, what properties they have. So that's all that's really important. All right, so that's good for this.